Happy 4th of July from the US of A, where not only do we celebrate flagpoles, we celebrate the poles of complex functions. I first learned about these analogs to the real value asymptote without really understanding where does this name poles come from. Like, for example, if you have a function f of z is z squared plus z minus 2 over z plus 1, we can use Mathematica to graph f. And here are two graphs. The vertical axis represents the absolute value, or the modulus of f of z, and the colors represent different arguments of f of z. And so you can see this weird looking cylindrical shape over here, this strange cylindrical shape that seems to be going off to infinity, and that's exactly what it's doing. In fact, f has a pole at this long tube. To show that more formally, we can factor z squared plus c up here, and then divide by z plus 1, and then subtract 1, add 1, rewrite this, and we get the Laurent series. This is the Laurent series of f of z about z is equal to minus 1. Since there's only 1, so there are finite many terms with negative exponents on the z minus 1, we say that f of z has a pole, in this case a simple pole, at z is minus 1. And that's the definition of a pole. It leaves out the visual fact that what a pole is it's like an asymptote, like from a single variable, like a real variable function. Maybe an asymptote looks something like that, right? This goes off to infinity, but since we can graph this complex valued function in 3D space, or at least its absolute value in 3D space, we can see that an asymptote turns into essentially, it's a pole, right? It's a big tube. It goes off to infinity, or more formally, you could say the limit as z approaches minus 1 of the absolute value of f of z, the modulus of f of z, is infinity. And so not only is this a nice visual way of understanding this is in fact why poles were originally called poles, but it's also a nice way of celebrating the 4th of July. Thank you for watching.